C1 e to the power lambda 1t plus C2 e to the power lambda 2t. So this is the solution, and C1 and C2 will be determined by the initial conditions. Now there are three scenarios created by this lambda. Let's discuss those three scenarios because the behavior of x with respect to time is going to be different in those three scenarios. So in the first case, c over 2m is greater than square root of k over m. So in that case, lambda 1 is equal to minus c over 2m plus square root of c over 2m square minus k over m, and lambda 2 equals to minus c over 2m minus square root of c over 2m square minus k over m. Now notice that this is negative and this will also be negative, right? Because this c over 2m square will be greater than k over m. So you will get a positive number under the square root, but that positive number is smaller in magnitude in comparison to c over 2m. So for that reason, this lambda 1 will also be negative. So if you look at the solution, x equals to c1 e to the power lambda 1t plus c2 e to the power lambda 2t, when c over 2m is greater than square root of k over m, both lambda 1 and lambda 2 are negative. Because of this, x will be an exponentially decaying function. So if I make a plot of x as a function of time, because we have e to the power negative some number times t, we will get an exponentially decaying function. So when time goes to infinity, this function will become 0. This type of solution is known as an overdamped solution. Okay, now let's imagine second scenario in which c over 2m is less than square root of k over m. Now what will happen to this when c over 2m is less than k over m? In that case, we will get a negative quantity under the square root. Okay, so let's rewrite lambda 1 and lambda 2 for this scenario. Lambda 1 and lambda 2 can now be written as minus c over 2m plus minus square root of, I'll take negative 1 as the common factor, and we have k over m minus c over 2m square. Now the square root of minus 1 is the imaginary number I. So this will give us minus c over t m to m plus minus I square root of k over m minus c over 2m square. So now if I want to write the solution for x, I will get x equals to c1, and lambda 1 will be, lambda 1 will be minus c over 2m plus I square root of k over m minus c over 2m square times t plus c2 e to the power minus c over 2m minus I square root of k over m minus c over 2m square times t. Okay, so this can be rewritten in the following way. We can write x equals to c1 e to the power negative c over 2mt times e to the power I square root of k over m minus c over 2m square times t plus c2 e to the power minus c over 2m times t e to the power negative I square root of k over m minus c over 2m square times t. So here we can take e to the power minus c over 2mt as a common factor, and we get c1 e to the power I square root of k over m minus c over 2m square t plus c2 e to the power negative I square root of k over m minus c over 2m square t. Now at this point we need to recall the definition of e to the power I theta. This is equal to cosine theta plus I sine theta. So if we substitute e to the power I by cosine theta plus I sine theta, then we will get a combination of cosine and sine here and combination of cosine and sine here. So they can be again combined, and we can write x equals to e to the power negative c over 2mt times a cosine k over m minus c over 2m square times t plus b sine square root of k over m minus c over 2m square t. You may notice that there are two types of terms here which depend on time. One is sinusoidal, so these are the sinusoidal type of terms, and another is exponentially decaying. So if we now make a plot of x as a function of time, we will get a sinusoidal function which is exponentially decaying in time. So if you track its amplitude, it will be exponentially decaying in time, but there will also be sinusoidal variations because of the cosine and sine terms. And the frequency of this oscillation is equal to the argument of these sinusoidal terms. So that's going to be w equals to square root of k over m minus c over 2m square. So this is the damped oscillation frequency. Now, in a system where the damping is 0, in other words, if c equals to 0, then omega equals to square root of k over m. So this square root of k over m is known as the natural frequency of the system. It is also known as undamped natural frequency. So this omega equals to square root of k over m, which we will obtain for frequency if c equals to 0, is known as natural frequency or undamped natural frequency. Now we need to note this because later on this is going to be useful to us. There is also a third possibility for lambda. So the third possibility is c over 2m is equal to square root of k over m. Now in this case, see, c over 2m is equals to square root of k over m. So the term under the square root will be 0. So there will only be one value of lambda. Lambda will be equal to minus c over 2m. So in this case, now again we will have to refer to our knowledge of calculus, and then we will obtain the following general solution for x. xt is equal to c1 plus c2t times e to the power lambda t. Now here again there are two types of terms which depend on time. So there is c2t and there is e to the power lambda t. And notice that the exponential term has a negative argument, right? So this power of exponential term is negative. So because of that, this exponential term will lead to exponentially decaying behavior. There is also c2 times t. So as time increases, this c2 times t will increase. It will become bigger and bigger, but the exponential term is going to be dominant. Okay, so because of that, x as a function of time will be an exponentially decaying function, primarily an exponentially decaying function. And this type of scenario is known as critically damped motion. Okay, so this type of motion is known as critically damped motion. This critically damped motion is in between the overdamped motion and underdamped motion, or this critically damped solution is in between overdamped solution and underdamped solution. Now, but this critically damped motion is important because we will obtain the critical damping constant in this situation, and this critical damping coefficient will be useful again later on as a reference for describing the behavior of the system. So in this particular case, in the critically damped case, C over 2m is equals to square root of k over m, or we can write c square divided by 4m square equals to k over m. I'm going to solve for the value of damping coefficient c, okay, for the critically damped case. So that's going to be c square equals to 4 km, or c equals to 2 square root of km. Now this 2 times square root of km is known as the critical damping constant. So this is your critical damping constant. And what is the advantage? Now we can define a damping ratio, which is the ratio of any damping constant or damping coefficient to the critical damping constant. So C divided by CR is equals to the damping ratio. So I can write any damping coefficient equals to the damping ratio times the critical damping constant. Both this damping ratio and natural frequency can now be used to rewrite the second order partial differential equation. How do we do that? So look at this C over M. C over M is equal to 2 times the damping ratio times the natural frequency. And let's prove that to ourselves. 2 times damping ratio. Damping ratio is C divided by the critical damping constant, which is 2 times square root of km, times the natural frequency, that is square root of k over m. So 2 and 2 cancel, square root of k and square root of k cancel out. We have square root of m times square root of m, that gives us m. So this will be equal to c over m. Now it is obvious that k over m is equal to square root of k over m squared. This is equals to omega n squared. So in this way now we can write the equation for this mass on a spring as acceleration plus 2 times damping ratio times natural frequency times dx dt plus square of the natural frequency times x equals to ft, where this ft is 1 over m times force.